concept of set serves as a fundamental part of the present-day mathematics. Today, this concept is being used in almost every branch of mathematics. Sets are used to define the concepts of relations and functions. The study of geometry, sequences, probability, etc. requires the knowledge of sets. The theory of sets was developed by German mathematician Georg Cantor. He first encountered sets while working on problems on trigonometric series. In this chapter, we discuss some basic definitions and operations involving sets. In everyday life, we often speak of collections of objects of a particular kind, such as a pack of cards, a crowd of people, a cricket team, etc. In mathematics also, we come across collections, for example, set of natural numbers, set of points, prime numbers, etc. More especially, we examine the following collections: odd natural numbers less than 10, that is 1, 3, 5, 7, 9. The rivers of India. The vowels in the English alphabet, namely A, E, I, O, U. Various kinds of triangles. Prime factors of 210, namely 2, 3, 5, and 7. The solution of the equation x squared minus 5x plus 6 is equal to 0, namely 2 and 3. We note that each of the above example is a well-defined collection of objects in the sense that we can definitely decide whether a given particular object belongs to a given collection or not. For example, we can say that the River Nile does not belong to the collection of rivers of India. On the other hand, the River Ganga does belong to this collection. We give below a few more examples of sets used particularly in mathematics, namely n, the set of all natural numbers; z, the set of all integers; q, the set of all rational numbers; r, the set of real numbers; z plus, the set of positive integers; q plus, the set of positive rational numbers; and r plus, the set of positive real numbers. The symbols for the special sets given above will be referred to throughout this course. Again, the collection of 5 most renowned mathematicians of the world is not well defined, because the criterion for determining a mathematician as most renowned may vary from person to person. Thus, it is not a well-defined collection. We shall say that a set is a well-defined collection of objects. The following points may be noted. Objects, elements, and members of a set are synonymous terms. Sets are usually denoted by capital letters A, B, C, X, Y, Z, etc. The elements of a set are represented by small letters A, B, C, X, Y, Z, etc. If A is an element of a set A, we say that it belongs to A. The Greek symbol epsilon is used to denote the phrase belongs to. Thus, we write A is an element of A. If B is not an element of a set A, we write B is not an element of A, and read B does not belong to A. Thus, in the set V of vowels in the English alphabet, A is an element of V, but B is not an element of V. In the set P of prime factors of 30, 3 is an element of P, but 15 is not an element of P. There are 2 methods of representing a set: roster or tabular form, set builder form. In roster form, all the elements of a set are listed. The elements are being separated by commas and are enclosed within braces. For example, the set of all even, positive integers less than 7 is described in roster form as 2, 4, 6. Some more examples of representing a set in roster form are given below. The set of all natural numbers which divide 42 is 1, 2, 3, 6, 7, 14, 21, 42. In roster form, the order in which the elements are listed is immaterial. Thus, the above set can also be represented as 1, 3, 7, 21, 2, 6, 14, 42. The set of all vowels in the English alphabet is A, E, I, O, U. The set of odd natural numbers is represented by 1, 3, 5. The dots tell us that the list of odd numbers continue indefinitely. It may be noted that while writing the set in roster form, an element is not generally repeated. That is, all the elements are taken as distinct. For example, the set of letters forming the word school is S-C-H-O-L or H-O-L-C-S. Here, the order of listing elements has no relevance. In set builder form, all the elements of a set possess a single common property, which is not possessed by any element outside the set. For example, in the set A, E, I, O, U, all the elements possess a common property, namely, each of them is a vowel in the English alphabet, and no other letter possess this property. Denoting this set by V, we write V equals the set of all X such that X is a vowel of the English alphabet. It may be observed that we describe the element of the set by using a symbol V. Any other symbol, like the letters X, Y, Z, etc., could be used, which is followed by a colon. After the sign of colon, we write the characteristic property possessed by the elements of the set, and then enclose the whole description within braces. The above description of the set V is read as the set of all X such that X is a vowel of the English alphabet. In this description, the braces stand for the set of all. The colon stands for such that. For example, the following set is read as the set of all X such that X is a natural number and X lies between 3 and 10. Hence, the numbers 4, 5, 6, 7, 8, and 9 are the elements of the set A. Let us now see some more examples of representations of set in two methods. That is, roster or tabular method and set builder method. First, the goal is to rewrite the quadratic expression, x squared plus x minus 2, as a product of two simpler expressions, called binomials. We are looking for something in the format x plus a into x plus b equals 0. The given set is described in set builder notation as the set of all X such that X is a positive integer and square of X is less than 40. To write this in roster form, we need to find all the positive integers whose square is less than 40. Let's test the positive integers one by one. Square of 1 is 1, which is less than 40. Square of 2 is 4, which is also less than 40. Square of 3 is 9. Again, this is also less than 40. Square of 4 is 16. This is less than 40. Square of 5 is 25. This is less than 42. Square of 6 is 36. Again, this is less than 40. Square of 7 is 49, which is not less than 40. Since the square of any integer greater than 6 will also be greater than 40. We stop at 6. The set of all positive integers that satisfy the condition is 1, 2, 3, 4, 5, 6. see that each member in the given set has the numerator 1 less than the denominator. Also, the numerator begin from 1 and do not exceed 6. Hence, in the set builder form, the given set is as follows.